students. I did not get as far into that last example as I would have liked, so let's keep going with it. So let's take polynomials over the reals, and this, we also discussed polynomials of a certain degree or less. So this would be polynomials of degree 2 or less. Okay, so what would be in here? Well, all the quadratics, all the linear polynomials, and all the constants. What are some vectors in here? Well, 1 would be a vector, because it's a polynomial in P2 of R. X would be a vector, very nice and simple one, and x squared. So, what would happen if I took the span of these three vectors, 1, x, and x squared? What would I get? And you can see that we are going to get all of P2 of R. And why is that? Well, because anything that's a quadratic or less is of the form ax squared plus bx plus c. So normally we use ax plus b if it's linear, and ax squared plus bx plus c if it's a quadratic, and we require a to not be 0. But if we're taking polynomials of degree 2 or less, we don't care if a is 0. So this is the set of this for a, b, and c in R. This is equal to P2 of R. So because of that, well, what do we have here? We have the span of three vectors, the vector x squared, the vector x, and the vector 1, because c times 1 is 1. So if I were to take, say, P3 of R, but I take the span of 1, x, and x squared in P3 of R, I'm not going to get all of this vector space, because ax squared plus bx plus c will never be equal to, say, 1x cubed, or 2x cubed, or 3x cubed minus 1, or 3x cubed minus x, or any of those polynomials, right? So because of that, because we can't get an x cubed out of this, no matter how many things like this I add and scalar multiply, it would always be of this form. And this is one reason that I've mentioned we're not multiplying polynomials, because otherwise we jump outside of these subspaces very, very quickly. But we can only add and scalar multiply, so we can never get to x cubed from inside here. So what do we have? Well, we have a vector space, which is P2. It's a P2, which happens to be a subspace of P3 of R. And this is true regardless of what the field is. P1 of F is a subspace of P2 of F, which is a subspace of P3 of F, and so forth, and so on and so forth. So here we have an example where we have a span so we have a span of finitely many vectors in P3 of F. But P3 of F would be in itself the span of 4 vectors. P2 would be the span of 3 vectors. And by the way, I don't need to pick these 3 vectors. I could have picked 3 different vectors. For example, if I wanted to pick the vectors, let's say I wanted to take the span of x squared plus x, x squared minus x, and 1 in P3 of F. And you know what, let's stick to R just to make things a little more concrete. I want to know that my minus is not the same as my plus, which it might be if it's an abstract field or an arbitrary field. So I have the span of these guys in the polynomials of degree 3 or less in R. So what is that span? Well, what do we have? I know that x squared plus x squared minus x is in the span. So let's call this W. So that's equal to 2x squared. And since W is a vector space, it has to be closed under scalar multiplication, including multiplication by 1/2. So I have 1/2 in W. So, and because I have 1/2 in my field, so I have x squared in W. And I also know that this has to be in W because we have the additive inverse of this, right? Because it's a subspace, so we have the inverses of each of the elements as well. So what do I know? What do I get here? I get 2x is in W, and since 1/2 is in the field, I get x is in W. So I know that x squared is in W, I know that x is in W, and I know that 1 is in W, so this generates the same thing. This span, this W, is also equal, we're in the rails, to the collection of polynomials of degree 2 or less. Of course, maybe I pick a span that doesn't give me all of that. For example, if I wanted to, let's let V be P3 of R still, and I want to take the span of x squared plus 1, 2x squared plus 2, and 3x squared plus 3, well, that's going to be the same as the span of x squared plus 1, because these are all multiples of x squared plus 1. So we're not going to get all of P2. We're not going to get P1 either. We're going to get something different. What is this equal to? This is going to be equal to the set of A x squared plus 1. So that A is a real number. Okay. What we're looking at, though, is we're looking at these vector spaces which are spans. And remember, built into the definition of linear combination is a certain finiteness, right? We're not taking infinitely many vectors. We're never doing this. We're never doing A1, don't look at this, or I look at it and never do it. How about that? Plus A2V2 plus A3V3 plus dot, 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 all the way out to infinity. Because what does that mean? Right? We haven't defined any measure of convergence. So we can't do things like calculus 2, where we have all those series tests for convergence and divergence here. We don't have any definition of the limit of a sum of infinitely many vectors. All we can do is we can add finitely many vectors. And we can add finitely many vectors because if you can add 2 vectors, you can add finitely many, because you could repeat that process finitely many times and then stop. The thing is if you try to make it go towards infinity, then you have to deal with all sorts of issues of convergence. So there's something nice. So this is bad. What was that? I don't know. We saw nothing. What we are studying is vector spaces. And if a vector space is a span, for some v1 through vn. I might not know what those vectors are. I might just be given a v, but if v happens to be the span of the vectors v1 through vn, for some v1 through vn, that is a new definition that is going to be important. Obviously, if I were to take, well, not obviously, no, definitely not obviously, but think about whether the set of all polynomials is finite dimensional.